Ladies and gentlemen, if you'd please adhere your notes to page 53 in your notebook, and we'll get started. Today we're going to be talking about the one sample t-interval for means. We're going to be going through the steps and an example similar to how we did last week. With a confidence interval, we will still use a four-step process, and we'll keep using this process over and over throughout the rest of the semester. With quantitative data, the process is very similar to as it was for categorical data with some minor tweaks. The first step is to name the interval. And because we are going to be working with quantitative data, this does require a slightly different interval, which has its own name. And so our step number one will slightly change because now we will be calculating a one sample t-interval to estimate the true mean of whatever our situation is. Again, that comes from the context of the problem. Step number two stays roughly the same with the same general conditions of needing good quality data and normality. More specifically, good quality data means that we need randomization, either a random sample or random assignment of treatments. With normality, we have some choices. Because it's quantitative data, it's not going to be quite the same as it was for categorical data. So one of the following must be met. Either the population is approximately normal, which is the situation that the jelly blubbers had, or our central limit theorem applies because we have a large enough sample size. Typically, n is greater than or equal to 30. This goes back to the applet, where the sampling distributions always ended up approximately normal no matter what the original population. Or if we have data, we can graph it to check and see if approximate normality is reasonable. This is where we used the normality plot the other day. Step number three is to do the math. The general form always remains the same. It is the point estimate plus or minus the margin of error. However, quantitative data has a slightly different formula than categorical. X bar plus or minus T star times the standard deviation over the square root of n. Again, you did this with the jelly blubbers where you found your standard deviation over the square root of n, and we'll be doing the same here. X bar is your sample's average. You may need to use one var stats in order to find that value. T star times a standard deviation over the square root of n represents the margin of error. So everything after that plus or minus is considered the margin of error. T star itself is called the critical value. That is from the t-table on page 8 of your notebook. With quantitative data, we will use the degrees of freedom line, and degrees of freedom is calculated as n minus 1. S stands for your sample's standard deviation. Again, you may need to use one var stats if this value is not given to you. And n is your sample size. Step 4 is your conclusion. This conclusion is very similar to what we had before. Based on our sample, we are blank % confident, so there's your 90, 95, 99, etc., that the true population mean of whatever the situation is lies between these two values. Looking at the example, says the following data gives the speeds in miles per hour as measured by radar of 10 randomly selected cars traveling on the interstate. Then you have some data. Construct a 90% confidence interval to estimate the true mean speed of all cars traveling on this highway. Like the other day, I'd suggest you pause the video after each step, try it on your own, and then unpause the video to check your work. Step number 1, we need to name our interval. We are working with quantitative data. These are values that are measured numerically that we could find a mean and standard deviation. So we're going to be doing the one sample t-interval. So step number 1, we will calculate a one sample t-interval to estimate the true mean speed of all cars traveling on this highway. Again, that context comes from the problem itself. Step number 2, we need to check our conditions. Our first condition of randomization. Do we have good quality data? We look at the problem, and it does say that it is randomly selected. So randomly selected is stated. We also need to check normality, and we have three options. Either number one, it says that the speeds are normally distributed, which the problem does not state. Number two, we have a large enough sample size that the central limit theorem applies. Unfortunately here, we only have 10 cars, so not over 30. So we must graph it to see if normality is reasonable. We actually have multiple graphs to choose from. You could do a box plot, a histogram, a stem plot, a dot plot. Normality plot is what we did with jelly blubbers. For this one, let's do a stem plot. If I look at my data, it goes from the 60s to the 80s. So my stems of 6, 7, and 8. And my leaves correspond to those stems. Now I need to determine if normality is reasonable. In other words, I want to know, is it roughly symmetric with no outliers? This does look symmetric with no outliers, so normality is reasonable. Step number 3, I need to do some math. So looking at my equation, I need to find my x bar and my s. So I'm going to use 1var stats to find the sample's mean and the sample's standard deviation, sx. T star comes from the table on page 8, and then the sample size is 10. So x bar from 1var stats is 74.2. T star, I'm going to look at line 9 for 90% confidence is 1.833. S is 5.308 from 1var stats, and 10 is the sample size. Calculating my parentheses, the 5.308 divided by the square root of 10, I end up with 1.679. Multiplying that times 1.833, I end up with 3.077. That is my margin of error. That is my leeway. So subtracting that from 74.2 and adding that to 74.2, I end up with the interval of 71.123 and 77.277. Step 4 then is putting that into my conclusion. Based on our sample, we are 90% confident that the true population mean speed of all cars traveling on this highway lies between 71.123 miles per hour and 77.277 miles per hour.